Okay, we have a series and we're going to find out if it converges or diverges. So with the limit comparison test, we have the limit as n approaches infinity, we have what we're comparing it to, and we have our original. So let's go and put our original in here, e to the n plus 1 over n e to the n plus 1. What are we going to compare it to? Well, we compare it to whatever is our original version, but stripped down to its essentials. So how do we do it? Its essentials would be pretty much if we just eliminate all the constants. And in this case, we can even eliminate e to the power of n and just have 1 over n, because that's really its general behavior, if you think about it, of this series. They are quite similar, besides e to the power of n, because you're plugging in a whole bunch of numbers, and yeah, that's gonna make this different than that one. Specifically, this one's going to be smaller. It's going to be smaller because you're plugging in a greater denominator. But, well, you also have a greater numerator. But yeah, I think that because you're multiplying this, you would get a smaller series in the end. But it doesn't matter. Like, this is the version of this that's stripped down to its essentials, because you remove this entire thing. You just delete that, and you delete this, and leave 1 over n. Just to capture the general behavior of it. So that's what we're going to do. That's our b sub n. And that's our b sub n. And now we could take the limit as n approaches infinity of that. But, of course, we have to multiply by the reciprocal, make that look nicer. So we would have n e to the n plus 1 over n e to the power of n plus 1. And why are we doing this? We're doing this to see if we can get something which is not 0 or infinity. If we get something which is not 0 or infinity, that means that the behavior of this corresponds to the behavior of this one. The behavior of that one corresponds to the behavior of that one. If that converges, that converges. If that diverges, that diverges. In the case when our limit to infinity does not yield 0 or infinity. So let's see. What is this? So now we can just divide. This one turned out to be quite easy. Limit as n approaches infinity, we divide n e to the power of n divided by n e to the power of n, because that's just our common thing we have in numerator and denominator, and it's the largest power. So n e to the power of n to the power of n plus 1 over n e to the power of n. We plug in infinity, these guys go to 1 anyway, so we would have this go to 0 because we have infinity in the denominator, so this would be 1, and this would also be 1. So 1 over 1 is 1, and 1 is not 0 or infinity. So we could have gotten any number as long as it's not 0 or as long as it doesn't go to infinity. And that means that whatever applies to this one also applies to that one. So let's ask, does this converge or does it diverge? Well, that's a p-series. If you don't remember, that's a p-series. It's specifically called the harmonic series. When it's to the power of 1, it's just 1 over n. But p equals 1. And if p is less than or equal to 1, then this diverges. This diverges. If you can't remember if it diverges or if it converges because you have too many things to memorize, then don't memorize it. Just reason about it. So if we had a p that was like really, really large, like say we had 550 or something, any really large number, our denominator is going to get very large, which means our term is going to get very small. And if your terms are getting very, very small, that indicates convergence, remember. And divergence is when you go to infinity, or when it doesn't exist. So a very small number would indicate, a very, very small number in the denominator would indicate divergence, because that would mean a very large number as a whole. So in our case, it's going to diverge. And because this equals 1, it's not 0 or infinity, this also diverges. Diverge.